I've been involved in the AMS experiment since 1994, when the experiment was first proposed by a team of European American scientists to NASA and to the various founding agencies. At that time I was working with Professor Samting on the L3 experiment at CERN, and we were discussing what to do next. And the idea of exploring the cosmic radiation with high accuracy with the revolutionary experiment of extreme sensitivity was developed in several discussions we had at CERN, at MIT, in various places, until we decided to design this detector and to submit the proposal. So we started many years ago, 1994. And after that, the proposal was approved within a year after review by various panels from US, from Italy, from France. And then we started developing the technology and building the experiment, which was flown for the first time in 1998, which was absolutely a very short time, absolutely a record time from the conception, proposal, approval to the flight. This is how we started. Next year, 2012, is the 100th anniversary of the discovery of cosmic rays. The cosmic rays, when they were discovered for the first time in 1912 by Victor Hess, they allowed to have a glimpse on completely different phenomena, and which were not possible to be studied in the laboratories. And thanks to the discovery of cosmic rays and the measurement and searches which followed, particle physics was born. And the first new particle which was found, a total of almost 20 particles were found, new particles were found in cosmic rays before the advent of the accelerators. And the very first one which was found, you guess what, was an antiparticle, was the first positron. So the cosmic ray immediately gave a tremendously important hint, which was the antiparticle, the antimatter, confirming the Dirac theory, opening a completely new world. So we hope to do exactly the same. 100 years later, but with a totally different technique, much more powerful, much more sophisticated, being in space and not on a hot air balloon like Victor Hess in the beginning of the last century. And for the first time, studying the composition of cosmic rays with incredible accuracy, 1 part in a billion, 1 part in 10 billion. It's like if it's raining over Geneva and you have one drop which is red and you catch it without hesitation and understanding there is something strange going on. Similarly, we are going to catch billions and billions of cosmic rays looking for exotic components, very rare one. And this was not possible to be done with previous experiments, either because they were on ground and then the atmosphere is degrading the cosmic radiation too much, or because they were small in aperture, or because they were in balloon which only lasted for a few days, for 1 day or few days. So AMS put together all these properties to be state-of-the-art with the most sophisticated detector ever built, to be large, so to catch a large fraction of the flux of cosmic rays, and to stay for many, many years, 10 to 18 years, catching those particles. In this way, we can look for the most rare components. Antimatter is an extraordinary property of matter, which is about being opposite. Being opposite, in particular, the charge is opposite, plus versus minus, or minus versus plus, or the angular momentum being opposite. And it's like looking yourself to a mirror your left becomes right, your right becomes left. You are opposite of yourself in a sense. All particles have been found, they do also exist as antiparticles. So it's a general property, it's a basic property. The little problem is that the two types of matter, they don't want to stay together. The moment they touch them together, they make a nuclear reaction, they flash in light, and they disappear in energy. Antimatter is studied and produced in laboratories like CERN, in hospitals for many, many applications, routinely, every day. So why we go to space? Very simple. We are looking not for the simplest antimatter, not for the simplest antiparticle, but the complex form of antimatter, like antinuclei of helium, carbon, oxygen. And the reason is very simple. The matter we are made of is a complex matter, and all the nuclei except hydrogen and a little bit of helium have been produced by fusion inside the stars. After the Big Bang, there was no oxygen, no carbon, no uranium. This has been built in the stars. So you see very immediately that the moment we see an anti-carbon or an anti-oxygen, there is immediate indication that somewhere in the universe there are a large amount of antimatter in the form of anti-star, building by fusion from lighter antimatter into heavier antimatter, and it will open up a completely new world, exactly in the same way like in 1932 the positron was found. With an experiment like AMS, dark matter can be searched in so-called indirect way. Dark matter, by definition, cannot be detected by a spectrometer, by a normal detector used for charged particles. But you can look for the fragments of annihilation of dark matter particles one to each other. Dark matter particles, they can collide, they can annihilate, there are theories predicting that, and producing secondary particles after they decay, after this collision. Those particles are normal particles, but this source of normal particle due to this annihilation is disturbing the normal spectrum of cosmic ray particle how we expect. There are tiny modifications, part in 1,000, part in 100, so it requires very much of a precision, of accuracy to detect them. But by looking to the shape of this distribution with respect to the expectation, we may see hints of annihilating dark matter, producing secondaries, which can be measured by AMS2. We go to space because the particle we are looking for, the cosmic ray we're looking for, they have energies which are relatively low, from GeV to 100 of GeV, and they could not make it through the atmosphere. The moment they enter the atmosphere, they get degraded, and they completely lose any significance, any meaning which can be traced back to their origin, either antimatter or the secondaries of dark matter. So it's mandatory to go to space to see the primaries before they interact with the atmosphere. There is a chapter of the physics of AMS which is about the phenomena which are causing the acceleration of cosmic rays. The phenomena which are explaining how they are made of different types, from the lightest one to the heaviest one. In the category of energies which are looking for with AMS, the study of the standard cosmic ray, the main component of cosmic ray, will tell us very much about the composition of the stars of our galaxy, how many nuclei, which means how much matter in between stars do exist to produce a secondary nuclei and so on. It's like setting the so-called background reference for the detailed measurement we want to achieve. Once you understand the standard cosmic ray physics, you can look for very rare events, you can look for distortion of the spectra for dark matter. So it's like making a reference to which compare. This type of searches is a mixture of the two. It is about astrophysics and particle physics at the same time, and we call it astroparticle physics. Is a field of research where Europe is extremely strong. Italy in particular has a long tradition into that. After 100 years of searching and studying the cosmic rays, which is astroparticle physics, we are still studying the cosmic rays to make fundamental discoveries. The collaboration of AMS is exactly shaped on the collaboration which are typically for CERN, for Fermilab, the large experiment at the Large Accelerator. A group of teams which are coming from different universities, from different institutions, driven by curiosity and with excellence in technical knowledge, in capability of building instruments. It's the only way to support this curiosity-driven big science. And it's the only way they can be supported for so long. Operating together for 15 years is really very difficult to achieve, can only be ensured by a common goal. And this is typical of this large international collaboration. As you know, in Europe, we do have a large contribution by Italy, France, Switzerland, Germany, Spain, Holland. And this was instrumental to allow AMS to be built. CERN hosted the integration of AMS for many years. CERN contribution has been really important for us to bring together this experiment, which is now in space, which now will be in space. So CERN, I say it again, CERN was really instrumental to allow this collaboration to bring together, to put together this large experiment in a very similar way as was done for the accelerator experiment. The only difference now, this experiment is ready to be launched and will be to space very soon. And they will be performed in a very similar way to how we are used for experiment operating at LIC on the previous accelerator, meaning taking data 24 hours a day by a team of scientists using computers and so on. And by the way, as you know, the payload operation center for AMS will be at CERN for the next 10 years or more. So CERN has shown to be of essence in the role of catalyzing the international community working on AMS, as it did in catalyzing the international community working on the LHC experiments. In this field of research, particle physics, you always are a collaborator, you always are a competitor. The two things are in a strange equilibrium. On issues like dark matter, we don't understand what dark matter is. So the community has understood that has to look in various directions. And then the luckiest one will get the answer. And maybe the answer cannot come from a single field, has to come from more fields together. It's fascinating. So we are both collaborating and competing. We are now very close to the launch. And obviously, I feel very strange. But the real, I've seen shuttle launching experiment built by me at least 2 times. This is the 3rd one. And the first thing when you see that the shuttle is leaving or the rocket is leaving, you feel relieved because it's too late to do anything more. You can only cross your finger, think how good or how bad you have been in the last several years building this device and getting ready to analyze the data. And I think this will be the same. I will be relieved and will now rush from Kennedy to Johnson Space Center, starting seeing the data coming down quickly, many, abundant, and starting looking to the distribution, to the plot, and to see that everything is okay, being prepared for a very exciting period of scientific analysis. AMS will be launched, and after 8 minutes will reach the space. The time to go to the atmosphere is only 8 minutes. Then will be switched on, but only for the purpose of controlling the temperature. For the following 3 days, we'll be orbiting around the Earth, getting closer and closer to the space station, and it will dock on the 4th day. There will be some activity by the astronaut by manipulating with this special crane and robotic arms, and then within a few hours will be installed in his final position. from that moment on, we're talking about the 4th day in space, we can switch on AMS, and within a bunch of minutes, half an hour or so, it will be on. And then within this time, the data will start pouring down, and the first reaction we'll have, they will come down at incredible speed, because it will be about 6 megabits per second continuous with peaks. And I tell you, we made a simulation studying how quickly the plots, which took for other experiments years or decades to accumulate, will accumulate with AMS in fraction of minutes, because the data intensity and the size of the experiment will be much, much higher than before. So, I mean, I think within a few days, the first raw distribution will be available. Before getting to the rare event, it will take some more time, maybe a few months. But if everything goes okay, we will have immediately a very interesting thing to look at, because the software is ready, the analysis is ongoing, the people are really charged to the maximum to start looking at the data. AMS is an example of a very inspirational experiment for the young generation. The people which have worked with us in these many years have learned about science, physics, of course. So they are motivated by the curiosity of making fundamental discoveries, but they also learned a wealth of knowledge, how to design detectors for space, how to operate with NASA, how to test this in extreme conditions, and so on. And they've been exposed to fantastic facilities at CERN, in Holland, by ESA, in Hestec, in NASA. They've been interfaced with many different culture, mentalities, organizations, and all of that in an experiment which is relatively small by the scale of today, very large experiment. We are probably altogether 500 people, but the core of the people which have worked together for these many years is probably about 100, 150, which is a small scale with respect to today's experiment. So I think this has been a very positive aspect of learning so many things and to live a so exciting experience in a context which was relatively human scale.